In this video, we'll look at graphing polynomials. So really important when we're graphing polynomials, you can pretty much read the x-intercepts off the factorized form of the polynomial. And if you ever have brackets that are squared or cubed, they should look like this. So singles cutting straight through the axis, doubles sort of touching the axis, and then triples going flat and then straight back down on the axis. If you ever want a really good example of a triple, what that looks like, y equals x cubed is a graph which looks like that. And if we did go to graph that on a calculator, you see it does go flat and then straight back up through. And if you want to be really precise about it, this graph here happens to have a value of a equals 0. X takes 0 cubed. But let's do a couple of concrete examples. So this one here has 3 x-intercepts. So the x-intercepts according to the equation, that first bracket will give us positive 1, the next bracket will give us negative 1, and the next bracket will give us positive 4. Remember, you've got to have like 4 take 4 would give you 0 there. So x is positive 4 in that case. So we'll pop those x-intercepts straight in. So I've got one here at 4, 1, and minus 1. All right, now for the y-intercept. And remember, by definition, this happens when x equals 0. So that is going to be y is 2 lots of 0 take 1, 0 plus 1, and 0 take 4 according to that equation up there. And then we can just sort of plug this in. 2 times minus 1 times 1 times minus 4 gives you positive 8. So if I have, let's say, 5 here on the y-axis, my y-intercept is going to be 6, 7, 8. Now this sort of forces your graph to have a particular shape because it would have to go up here in between those 2 points to the y-intercept and then sort of back down and up through the other one. So cubics will only sort of turn around twice, so to speak, like you can expect two vertices. And it's basically forced to have this up, down, up shape because of where the y-intercept is. Now we should probably graph it and double check. Now if we do graph it and have a look, you can just see in your calculator, it looks pretty much like what we said there. All right, next one, we're going to have a double intercept. So really importantly, the x-intercepts we can read off the fully factorized form. So it's going to be x equals 0 from that first bit there. The next bit here is going to give you minus 3, but really importantly, that is a double because it's the squared bracket there. And then x equals positive 1. So we'll go and do maybe a similar scale for this. 2, 3, 4, 5. And 1, 2, 3, 4, minus 5. We'll plug in those x-intercepts, 0, minus 3 is the double, and then 1. And then usually what we would do here is find the y-intercept. But if we try and find the y-intercept, we're actually going to run into an issue because that's just going to be 0. Then that's not going to give us any information about how squished or stretched the graph is. So maybe just to get an idea of what this looks like, we can look at another point on the graph. So we probably shouldn't pick any of our x-intercepts because that's going to give us 0. Maybe let's just pick x equals minus 1, just for an example point. So if we get that, y is minus 2, lots of minus 1. Minus 1 plus 3 squared, and then minus 1 take 1, which we can work out. So that is 2. It's 2 squared, and it is minus 2. So that all up is going to give us minus 16. So we know that sort of down here we're at minus 16. So maybe on my scale I should go, let's say 2, 4, no, let's go 10. We'll go minus 20. So minus 16 can sort of be down here, and that point there that we just worked out is at minus 1, minus 16. All right, if we continue on our graph, the graph did have that double at minus 3. So since it's got to come down here to hit that point, I would expect that the double looks like it's come up and then gone flat at minus 3, and then come back down and up through that point, something like that. And if we go here, these are singles, so they're going to cut through the axis, and then we'll come back down. So this is a quartic function, which means that it has 3 vertices. So it's always 1 less than the degree of the polynomial. And if you think about why that's true, you can actually use some calculus to justify it. Because if you've got a degree 4 and you differentiate that, you'll get a degree 3. So this is f dash of x. We would expect f dash of x equaling 0 to be the flat bits. So on a degree 4, I would expect 3 flat bits, which we have. So that's good news. Again, let's just graph it and double check. All right, now if we draw a graph, there we go. Looks pretty much like what we said. And if I go trace at -1, I'm hoping that I got that -16 value that we talked about. Excellent. All right, then you can go in reverse. You can be given an equation, given a graph, and you need to find the equation. So here, these are cubics, by the way. So they're going to look like a, and then x plus 3 will be our first factor because that's the first x-intercept. Next intercept is at 0, so I might actually just put a normal x there out the front for that one. And then we're going to have x take 5. And we also know that if I sub in 3 for the x value, I should get -6 for the y value, and that can help us figure out what a is supposed to be. All right, and then we'll just chug through this algebra. So that's a times 3 times 6 times -2. So that is -6 equals, actually what I'll do, I'll be a little bit cheeky. Cancel that off both sides, so we're going to be left with -1 is a times 3 times -2. So -1 is -6a, therefore a is 1 over 6. So y would have to be 1/6 x, x plus 3, x take 5. Now, as per usual, we're going to type that into our calculator in graphing mode and then hopefully check that our graph looks the same there. And it's not a bad idea to trace at 3 and make sure we get -6, which we do. All right, next we have this graph here. This is also a cubic graph. So really we need y equals a. Now this first intercept is going to be x plus 2. And then the next intercept has got to be, well, 7/2. So I like to go 2x takes 7, because when you solve that you get 7/2. Now I have purposely made a mistake there. I'd be very interested to know if you can spot what it is. If not, I'll tell you now. I've missed the squared on that bracket there. Because this was just touching it and coming off, that's a double intercept. All right, now I can just solve. So if I plug in the point 0, 14, because that point there is 0, 14, I should be able to get it. So let's plug in all those values and see what we get. That's a 0 plus 2 squared, and then 2 times 0 takes 7. So 14 is 4a times -7 essentially. So let's make sure we get this right. 14 is -28a, therefore a is -1/2. So we'll type out that equation, so -1/2 x plus 2 squared, and 2x takes 7, just like that. If you want, you could have had this bracket as x take 7/2, and if you did that, you would have got -1 as your a value. So just be aware that that is an option. But let's graph this on our calculator and see if we got it right. All right, so there's our equation in the calculator. We've drawn it, and if I trace at 0, I should hopefully get 14, which I do. And next up, we just have this one, which is a worded problem, but it's the same sort of process. So the x-intercepts tell us x take 2 is a root, x plus 1 is a root, and x take 3 squared, because it's a double root, is a root. So then we're going to do this one. Y is 24, x is 1 in all spots, and we'll sub that in and see what happens. We also need an a there because we've got to work out what that scaling factor is. All right, and if we do that, we should get 24 is a times -1 times 2 times -2 squared. Or in other words, 24 is a times, let's see, 3 negatives. So a times -8 essentially. Therefore, a would have to be -3, and that tells you that y is -3, x take 2, x plus 1, and x take 3 squared. And we just graph that and see if it works out. All right, so I've typed that equation in here. We're going to draw it. So what we should be seeing is if I go Shift-G, solve and root, we'll have, -1, 2, and 3. And then it should pass through the point 124. So if I trace it at 124,